All right, if everything worked according to plan, you should be seeing a list of problems. So this is going to be a PFG. On this one, I will work it behind you so you can double check and see how you did. You can print this out or you can just do it on another sheet of paper. Either way, take a picture and submit it to the chemistry inbox by the end of the day. And by the way, I see that there is approximately half of the chemistry students online right now. Please do not give the answers to the other half. Yeah, they can go to the recorded copy tomorrow and do it themselves from the recorded copy tomorrow. Also, by the way, if you didn't print it out, if you're just writing it down on another sheet of paper, then the circle part will be different unless you write the whole formula, and I'm not going to require you to write the whole formula. So I did every row with a different color so that there would be no question, like right here, if these go together or not. Different color means two different problems. So as review, I will do number one, and then I'll give you a minute to do number two, and then I'll write it down. And if along the way you're not seeing it, you have questions, then you can certainly, well, you know where the raise your hand button is. All right, so number one, circle what is not CNH, regular CNH, which is right there. And number two, state what it is. Well, it's chlorine. Chlorine is a halogen. And you might not know right off the top of your head that chlorine is a halogen. So you say, well, no, it's not an N, it's not a double bonded O, it's not an OH, it's not an O between two carbons. Well, the other thing is halogens. Let's see if chlorine is in the halogen group or not. I guess that's how I'd work it out if I didn't remember Cl was a halogen. But anyway, that makes this a halide. Now, you go ahead, try number two. I will give you just, it shouldn't take you too long. I'll give you a minute or so, and then I'll work it out, and you can check. And you got it wrong, you can fix it and still get full credit. I guess I could have used to put some more room in this one. Space them out a little more. Try to remember that for tomorrow. you can keep working right along. Some people get done faster. Some people get done more slowly. Get done fast, that's fine. Had to squeeze that one in there, didn't I? Carboxylic acid. Uh-oh. I is not N or O or OH. So the other choice must be a halogen. Oops, I skipped 6. Shame on me. Should make that and amide. All right, number 8 might bug you. Some of you will undoubtedly be bugged by 8. So that part you're good with. But the question is it an end or not an end? And it turns out that it is not an end carbon. I mean, wrong, 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 wrong. Turns out that it is an end carbon. Now, I know it's in the center from left to right of the picture, but let me make you a model of this. Maybe. All right, let's see how this, remember how to do this. Stop share, turn on my camera. All right, so here is that atom, except I didn't put all the hydrogens in. We've got basically one on the left, one on the right, and one on top. I didn't put all the hydrogens in here because I want you to see something. All right, so what's the difference? Still, two hydrogens. Which one's the end? There's three ends. Three that don't have anything else connected. So this is an end carbon. And the compound in that diagram would be the double bonded O on the end carbon right there. And so that somebody's going to ask anyway, what did I do to my forehead? I was working under a machine and I picked my head, moved my head too fast and hit something. All right, back to these problems. So this is on an end carbon, which would make this aldehyde. All right, number 9. Hopefully while I was building that, you got all done. So we've got the O and the double bonded O. O and double bonded O on the same place, or they have a carbon in common, however you want to put it. And that would make this an ester. Yes, Jonah?
For number 6, isn't like N on O, a double bonded O on a C, and an N on a C? Wouldn't that be a amide?
Isn't that what I put?
You put aldehyde.
No, aldehyde,
Oh,
they're above the number.
oh, they're above it. Okay, never mind then.
Whoops, little, it's gone. Yeah, writing above, in retrospect, may not have been the best thing. All right, here, number 10, we've got a double bonded O and an OH. On the same carbon. Uh-oh. Now I'm going to have to go below. I just don't have enough room to write here. So two, we've got a double bonded O and an OH on the same C. And that's the tricky part. We've got an N only on its C. So that means that there are two things going on here. This is a carboxylic acid. And an amine. So we've got two things there. Sid.
I got another question about number 6. So the nitrogen on the end has the two little stick things poking out of it, the two, I forget what they're called, but would that make it an amine and an amide, or would that just still be an amide?
No, the H's, that sticks stand for H. And in amines and amides, and in a few other cases, H's can be the R group. So if we look, now if I have this sharing right, yeah, I'm just sharing the screen, so that's switched over. So if we look here, that's the R2 right there. So we've got N, H is one of the R's. The other line is an H, which is the other R. And then we've got the C double bond O and the rest of it up there. So sticks can be R's. In this case, not in most cases, but not every case.
Okay, thanks.
All right, so get those copied down if you haven't yet. There's the end of it. Hopefully you got them all right doing it yourself, or most of them anyway. Take a picture of your work, submit it to me. Remember, people who missed it don't really deserve to have it given to them. So well, people who weren't here will have to just let them watch tomorrow when it's saved and turn it in tomorrow. They don't even take points off if it's a day or two late. All right, this brings us to the notes. Now we've been talking about the carbohydrates. So in carbohydrates, we had the monosaccharides, which are single sugars, one ring. Remember this. I don't plan on writing this every single time, but I'll do it one more time. And that should be even on, look the same on both sides. I'm pathetic. So it's an individual sugar molecule. I have not stressed yet what these are used for, so I need to do that. These are used primarily for energy transport, like glucose in your blood, or for short-term energy storage. And let me point out that this is usually very short-term energy storage, minutes to hours frequently. Disaccharides were the double simple sugars. So there was the 2 rings connected to each other. So it was double, 2 sugar molecules hooked together. By the way, they become 1 molecule when they're hooked together. Okay, these are used primarily for short-term energy storage. A little bit longer maybe, like maybe months instead of hours or days or weeks. I guess I'm not going to get really picky about short-term versus very short-term. Whoa, 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 whoa. What are you doing that to me for? And then we had the polysaccharides, which were the complex carbohydrates. These are up to hundreds of rings hooked together. Long chains of monosaccharides, usually glucose. It may be always glucose, but one thing I've learned in science is as soon as you say always or never, there's going to be some obscure exception. Okay, these are used for medium to long-term energy storage. By long-term, we could be talking months to, in some cases, years. Starch, that's the kind of starch that's in starchy foods. It is the starch of starchy foods. Glycogen is sometimes called animal starch. This is how mammals and probably other animals store in the liver with glycogen. These are also used for structural components. Structural components means they're used to build things, to give strength, like chitin in fungi and insect exoskeletons, and cellulose. Okay, so fungi and insects, and cellulose in plant cell walls. So cellulose is what makes up wood. That's why trees can be as big as they are and not easily tip over, not bend easily, except when they're very young, very still a bit flexible. It's, yeah, what makes wood. That's why wood is a good building material, fairly strong. I mean, not as strong as, let's say, steel, but a lot cheaper and still fairly strong because the cellulose is a structural component. All right, so that finishes up carbohydrates, and it brings us to proteins. Now, I cannot stress adequately how important proteins are. I mean, everything is important. I tried to stress this to you in biology when we were talking about this last year in biology. I cannot, just cannot adequately stress how amazing proteins are. proteins. Yeah, sure, they're muscle. They make up muscle and hair and bone. And they function in every stinking cell in your body. Several different proteins function in every cell in your body. Proteins are just amazing. They're complicated. They do a lot of stuff. And if they're going to be highly flexible and be able to do lots of things, they're going to have a fairly elaborate design. And that is what we're going to be looking at soon, their elaborate design. But anything that gets done, maybe, hopefully, you know, I can always wish that you remember this from 10th grade. Anything that gets actively done in a living thing is done by proteins. So by actively done, I don't mean like the chair is holding up the books you set on it because the chair exists. I mean, like, you are holding your hand out and holding up the books that are set on them, and you have to physically work at it. And if you quit working, your hand would drop and the books would fall to the floor. So everything that gets actively done in a living thing is done by proteins. Growth, done by proteins. Nerve cells, nerve impulses, I mean, done by proteins. Digest your food, done by proteins. Fight disease, done by proteins. Everything that's actively done in a cell gets done by proteins. Now, I say that because I think it's valuable to understand how amazing they are. It's actually valuable for a Christian to understand how amazing they are, because amazing design implies amazing designer, which, by the way, is why I just can't fathom how a person could look at this design with an evolutionary viewpoint and say, how amazing that this developed by itself. It seems like it would be impossible, and yet it happened. Well, when you say it seems like it would be impossible and yet it happened, you're saying that you've got some bias that you need to deal with. So proteins, but the other reason I stress this is because they're going to take some attention and some thought in order for you to keep them sorted out when we go into them tomorrow. So there's an online quiz. Please take it. PFG, please get it emailed to me. Folks who weren't here need to watch the video tomorrow and copy it down. Please don't just give them the answers. They need to follow along and try to get it done ahead of me. Other than that, we'll see you tomorrow and have a good day.